All right. Hello, everyone. Good morning. Good morning. We have 4 classes remaining. That's it. 4 classes remaining. On the board, you all can see the multiple choice grades. I was very happy with these. So you all can see that the average was a 68.5. There it is. The distribution looks all nice and all that jazz. There was not a single question that less than 45% of people got right. So that's why there was no curve. Curves are only done if there's a question that a lot of people got wrong, and a lot of people are usually less than 40. It means that only that less than 40% of people got it right. That's generally how I determine if there's questions in that category. There was no questions that fit that. So yeah, very happy with this. I am grading the free response. I won't be able to talk about the test in detail until after today, because I have a couple makeups, and then this will be tomorrow after my makeups today. So roughly around 12:30, 1 o'clock, I'll post the solutions for test 2. So I'll post them basically as soon as I can. It'll have the workout, it'll have all the answers to all multiple choice, it'll have the workout answers to the free response. I'm currently grading some of the free response. I grade a subset of them to give me a basis with which. So the graders currently have it. The goal is that the graders will be finished with the grading by next Thursday, so a week from today. I grade a subset of the exams, and I use that to standardize the grading. So I make their distributions look like my distributions. But they're looking like the multiple choice, which is to say decent. Some people did a really good job, some people did middling, some people didn't know it. But the majority of people at least showed they understood something, and then a decent amount also know what they're doing completely. All right, but again, I won't get into specifics for any individual question at this time. I will talk about the specifics very briefly on Tuesday, specifically which areas I saw the most mistakes in. But that's on Tuesday. All right, so there is that. I mentioned we have 4 classes left. So we have today. I don't think there's anything here else. All right. Get rid of everything. All right. So we have today. We have this coming Tuesday. We have the Thursday after that. And then we have the final Tuesday of Thanksgiving week. Here's the plan. The plan is to spend the next 3 classes doing electromagnetic waves. I'll try to justify why we're doing electromagnetic waves. I think I have a pretty good justification for it. One is in the catalog. And then that last Tuesday will be a review day. Now, I'm going to tell you that Tuesday is honestly not, so like, yes, I'm going to be here. Yes, so we're going to be reviewing. I am not making a new review. For the test final review, there's not going to be a new review. Why? Because I've already made 2 reviews. I say that. I will make like a 3 or 4 or 5 PowerPoint slide doing a quick review of electromagnetic waves. Otherwise, all the other review exists. You all want a review on everything from test 1? It already exists. You all want a review on everything from test 2? It already exists. You want a bunch of practice problems? Test 1 is out there. You want a bunch of extra practice? So all that to say, I'm not going to be generating a bunch of new resources for you all. I will maybe take one giant PowerPoint with all the quicker questions in it. How am I going to do that? I'm going to take the one from test 1 review with all the quicker questions, take one from test 2 review, and just put it all together. So all that to say, all the resources, 80 to 90% of the resources you want already exist. And the last thing I'll mention before I answer any questions, the most common question I get is, how much of the test is going to be on electromagnetic waves? About 1/10 of it. Why? Because it's about how much time we're going to spend on this. The amount that each subject will show up on the test is proportional to how much time we spend on the topic. So if we spend a full week on that, take that week, divide it by how many weeks we taught stuff, which is about 12 weeks or so. This we're going to be covering for 1.5 weeks, so you can kind of do the math there. So this will not have an over-representation. This will be as represented as every other topic that we kind of covered. Yes? Yes, great question. Problem set 3 is only on this. This is the only thing remaining, so problem set 3 is just what's left over. And there's about 22 questions in it or so, which may feel like a lot. It's because it's a week and a half worth of content. There's only one more quiz left. That quiz will open next Friday. I might open it a bit soon. Well, no, next Friday should be okay. And that'll be due the day of the exam. There's no reason for me making the quiz due after the exam, because the whole point of the quiz is to prepare you for the exam. Yeah. There is no AC circuits. I made a PowerPoint. It's posted on there if you want to look it through, but no, I will not. We don't have the time to cover it, so I'm not going to test you on it.
Does this include like the electromagnetic spectrum and stuff?
Very briefly. Very briefly.
The recitation for this week, was it always business that was
Was there no activity or was it on AC circuits?
Yeah.
Still do it. This is actually probably a good reason to attend it. You'll still do the recitation just because it's the same. The reason, so this week recitation is on AC circuits, I believe. Still attend it because what the recitations are basically the same across every class. So that's why we still have one on AC circuits. Every 2049 class, for the most part, does the same content every week. And I've been aligned with it. This is the one content we didn't get to. If your recitation was on Veterans Day, I will excuse the attendance. All right, so let's get into waves. And one more question. Electromagnetic waves will, if you consider photonics as electromagnetic waves. Everything in this PowerPoint, everything in problem set 3, yes. All right, so electromagnetic waves. First, I'm going to try to convince you this is important. Right now, you all exist in a soup of electromagnetic waves. You may be like, what do you mean by that? Every single wireless signal you all can possibly think about is an electromagnetic wave. The light that you can see is the most common one that people think about, but Wi-Fi signals, phone signals, Bluetooth, radio waves, all of those are all around you right now. And every single signal, again, it's a soup. They're all mixed together. And they're all like, so the field is incredibly complicated. What's really cool is there's electronics that can isolate it. So yeah, if you all are browsing the internet and you're picking up a signal, your phone needs to know how to pick up that signal. For you to be able to understand how any of this works, we need to understand waves, because these are waves. And if you don't understand what a wave is, then you cannot understand how wireless signals work. Not in any significant way. So we're going to use, there's some cool simulations I'm going to show you all for waves. There's a website that I'll mention a bunch of times in here that's really cool. But it's going to be a bit mathy. I say that. It's going to be a bit mathy. The derivations are going to be where a lot of the math is. The final results are not that complicated. The final results, the few equations I'm going to show you. In fact, let me just show you what those equations are now. Remember, the formula sheet is a great summary of everything I've taught you. And I've updated the formula sheet. Everything is up to date. This PowerPoint is completely up to date. The formula sheet is up to date. Problem set 3, up to date. Everything is finalized at this point.
Are you doing any more AI assignments?
It's a good question. Currently, I think the plan is no, but there's a caveat. Maybe. All right. Here is the last equations I'm going to teach you all. These last 2 rows. So to derive these, it's going to be a little bit mathy, but the equations themselves are actually not that complicated. I mean, maybe they look complicated to you at first, but I'll try to convince you otherwise. We have C equals E over V. We have V equals F times lambda. This is going to be called the wave function. That's the one that's probably the most complicated looking, but we need to understand that. Intensity. M equals C over V. Honestly, this last row is the simplest one. That's the one we'll cover on the last day. So yeah, we're going to go through these. However, there is one more equation. Is it on here somewhere? It should be. You all also do need to remember this one. This is going to be related. You'll see. You'll see when you see. All right. I do hear a decent amount of chatter in here. Look, I'm okay if you talk to your neighbor, but if I can hear you, that means everyone can hear you, and that can just, I know, be distracting. So if you want to talk to the person next to you, it's fine. Just, again, if I can hear you, it's probably a problem. All right. So here's what we're going to talk about. We're going to talk about why light's an electromagnetic wave. Before we get to that, we're going to actually just talk about waves, what they are. Define electromagnetic waves, relation between wavelength and frequency, electromagnetic spectrum, how light bends. It's going to be great. The reason we are doing this at the very end is it's an electromagnetic wave. We needed to understand electric fields. We need to understand magnetic fields. You literally can't cover this topic until the end unless we just hand wave it. This is probably one of the best rationales. Remember I told you all we introduced fields and I said, are they real? I don't know. They're very useful. Light is probably one of the best kind of evidence that fields may or may not be a real thing, because we just straight up say light is a field that oscillates.
Is light the fastest thing in the universe?
Light is, yeah, we'll get to that. Someone asked about the speed of light, as fast as it is. All right, so great. First thing I just need to tell you all, light is a wave. I'm going to prove, this has been proven through experiments. But for now, I'm just going to straight up tell you light is a wave. I'll mention some experiments later on that kind of prove this using some simulations. But yeah, everywhere in the signal you all can possibly think about as a wave. What is a wave is that hopefully, you all do have a decent understanding of waves is, but I'm also going to tell you it's not a full understanding. It's very unlikely, and that's what my goal is, to teach you what a wave is in a more rich way than you probably currently understand it. Because I'm saying here you need to understand waves. You're like, I understand waves. You know, we live in Florida, there's the beach, waves, they go up and down, all that jazz. But you're going to see real quickly when we dive into the math of it that there's more we need to understand than you currently understand. But you all do have a lot for me to lean on. Okay. Reminder, this slide is not necessarily a new slide, though things are written a little bit differently. A wave is just something that repeats itself over and over. If you think of what a wave does, it goes up and down and up and down and up and down and so on and so on and so on. It's periodic motion. Periodic motion is anything that repeats itself. So you need to remember some variables that we've talked about before. You need to remember angular velocity. That's going to come into play. That's the rate of change of the angle. You need to remember regular frequency. They're different but very much related. And period is what I probably should have had in the previous slide. I've included it now. Period is the time it takes for one full cycle to happen. So in the case of a wave, it's the time it takes for one full wave to pass. These are just general vocab words and variables that we need to be familiar with.
I thought the frequency was in hertz.
It is in hertz. Yeah, so the question was, I thought frequency was in hertz. You are correct. In fact, angular velocity and frequency both have the same units, which is a pain in the butt. They both have the same units of hertz, and that's why I generally specify, I have to say in words which one I'm using. The unit is not sufficient. Cycles and radians are not actually units. They're like quasi-units, which is a pain in the butt, but it is what it is. Oh, yeah. Is there a type? Let me think about this. Yeah, this is, I copied and pasted, I fixed the typo last time, but I sadly didn't fix it here. Thank you. Frequency is omega over 2 pi. Algebra should be correct. All right, so great. This isn't anything new, hopefully, but these are things you need to know. All right, so what is a wave? Again, this is something you're probably familiar with, but we're just going to formally define it. It's a disturbance that propagates or moves from the place it was created. So it's something is changing, and whatever that changing thing is, moves. So if you think of like an ocean wave, the water, goes up and that wave moves. Sometimes these waves carry, actually I'm just going to go ahead and make things simple. Pretty much these never carry material. Waves pretty much never carry material. They pretty much always carry energy. That's what they're transferring from one location to another. So even in the case of sound requires a material to move from one location to the other. But when I'm talking to you, it's very easy for me to prove that I'm not transferring the air from my mouth to your face. If I was, every time I'd be looking at you, you'd feel a blast of air hitting your face, and you don't. So what happens, I talk, they wiggle, that makes the next one's wiggle, next one's wiggle, next one's wiggle, next one's wiggle, so on and so forth. So even waves that require material don't transfer material. Ocean waves do not transfer water. You may think they do it, and in a very small setting, they do make the water move, but water waves do not transfer water. All they do is they make the water kind of go in a circle. It's very easy for me to prove to you that water doesn't transfer water, that water waves don't transfer water. If they did, then the shore would eventually, the waves keep crashing into the water, into the shore. If it transferred that water, eventually the shore would be covered with water. But it doesn't. It's just awesome. The waves come in, the waves go out. The waves come in, the waves, it oscillates.
With a photon and light, is that photon?
So I mentioned the word photon. You'll notice I won't use the word photon actually too much in this. A photon is what we call a wave packet. So it is a wave in and of itself that is moving. Which is a funny little thing. Ooh, yeah, if waves move energy, so we won't get to standing wave. It's great. Standing waves are where in space it makes it kind of oscillate. So in that case, it's not necessarily moving it from one location to another, but yeah, it's a tricky question, actually. I have to think about that more. Usually standing waves exist where they are, and they don't actually move around. That's a good question. I'll have to think about that more to answer that better. All right, so waves have a lot of interesting properties. This is all to prove you all that light is a wave. We're just basically going to use this simulation and look at a bunch of scenarios that you know that light does, and you'll see with waves that they do those things. So they spread in all directions, they bend around corners, they constructively and destructively interfere. So I really love this website. This website actually has a ton of simulations. We're just going to look at this one. So this website's super cool because it's a nice little visualization of a wave. All these little bright spots are the high points, the dark spots are the low spots. You can see it in 3D, which is kind of cool. It gets a little messier, you can play with things. So this is the simplest. This is a point source generating a wave. So it generates a wave, the wave spreads everywhere. What's cool with this is you can do, again, there's a whole bunch of examples, and we're going to kind of reference some of these throughout the thing because I think they do a really good job of showing stuff. So for example, waves bend around corners. Here's a wall. You can see that the wave bends around this corner. And you all know this when you all, for example, have your door cracked and the light in the hallway, it fills the room. Even though the crack of the door is only a thin little slit, the whole room gets a little brighter. Because why? Because light's a wave. You also see some interesting, this is our constructive and destructive interference happening, where you get basically these two, it turns into actually 2 point sources on the edge. And if we do the 3D view, it looks really messy, but if you kind of move it around, you can kind of see these funky things. It's fun. The other one, and I'm not going to really get too much into this, but this is a classic experiment in physics that proves that light's a wave. We call it the double slit experiment. So I know this is kind of weird to see here. So what I'm going to explain, you have a light source. We call it a plane wave. So it's think like an ocean wave. It's a big wave that is traveling along the plane. So just think of a big ocean wave. It's not like a single point source wave. It's this big flat thing. So we got this big flat wave up here. And it's maybe a little bit easier. Again, you can move stuff around in here, which is super cool. So you can see here these kind of plane waves, and it gets a little messy with reflection. So just don't worry about that. So you can see it coming on in. When they go through these two slits, what happens is you get 2 point sources, and you get this constructive and destructive interference. Parts where the waves add, parts where the waves subtract. If we I don't know if I can zoom in. I don't really zoom in here. But each of these acts like a point source, and they interfere with each other. This is why waves are so waves do these things. And it's super important for us to understand them if we want to understand anything about wireless signals. And a lot of things act like waves. So you can see it there from the side and so on. So, I think that pretty much covers all the things I wanted to show there. But play around with it. There's a lot of cool things there. Yeah. All right. So, characteristics of waves. This is stuff you probably learned in middle school, high school at some point in your life. Every wave is an amplitude. That's how it's called. Actually, I have it better defined out here. Amplitude, frequency, and wavelength. Wavelength is the distance. You often will hear the word distance between two peaks. Better definition is the distance between, this is not even ideal. It's the distance between two identical points, though you do get into some problems there. You all know what wavelength is, hopefully, so I'm going to actually improve this definition for future. But You know, if you have some wave, it repeats itself. The wavelength is not the entire wave. That's not useful for us because these waves can travel for forever. If you all shot a wave into space, it's going to go forever. We're not going to measure from infinity to where I started. That's nonsense. What we're going to measure is the distance between some point and some point such that I get the entire wave. The wavelength is the length required to get the entire wave. The entire, and it repeats itself over and over and over. The variable is lambda. Lambda, I think, we've used this before for density, linear density. We're using it again for this. The trick to this is you start kind of at the top of the hill, and then you just give it a little leg. Lambda, units of meters. We mentioned frequency before. Frequency is how many times does this wave fully oscillate per second. You can almost think of it like you saw these ocean waves going by you. How many times does the full wave pass you? If the frequency is 5 hertz, then every second I see 5 full waves. If the frequency is 1,000 hertz, that means every second I see 1,000 waves. If the frequency is half a hertz, that means I see half a wave every second. And the amplitude is not how tall it is. I mean, that's another hand-wavy way of saying it. It's the maximum distance from the equilibrium. So, you know, amplitude can be up or down. Again, none of this should hopefully be too new for you all, but it is variables we're going to be working with. So I want to make sure we're up to speed in case you haven't seen these. So, again, classic middle school, high school things. Yeah?
Is wavelength the same thing as the period?
That's a good question. Is wavelength the same thing as the period? The period is the time for one wavelength to pass. That's a great question. So the period, wavelength is distance, period is time. So that's a great question. Period is the time it takes for one wavelength to pass, one full wave. Yep. And it's the inverse of frequency. Yeah. Which is a really useful thing. If frequency is how many waves you get per second, if you want to know how many seconds per wave, it's just the opposite of that. You can look at the units and kind of see that. All right. Great. Let's see. You know, again, I'm assuming things about your all background on this. Let's see if you know how to find wavelength. Should be. No, you're right. I didn't put it up there. The right answer is not up there. Let's change all the numbers so you don't know which one it actually is. Silly me. Hey, I'm glad it worked out great, right? Alright, there you go. What is the wavelength of the following wave with the updated answers? The right answer wasn't there. Now it is. So I got a wave here. The displacement is measured in meters, and the horizontal direction is also meters. I didn't try to throw any weird units in there. Give you all 20 more seconds. In 5, 4, 3, 2, 1. All right. To find wavelength, there is an infinite number of ways to get the right answer. You pick a spot on the wave. So let's say I pick right here. I then find the next spot that is identical to it. Now, when I say identical, it doesn't mean the same value. It means the same value and the same slope. I need the entire wave. If you picked, for example, this spot, and you said this is the wavelength, that is not the entire wave. That only has the up part. You need the up and the down. So you could pick this spot and this spot. That is the wavelength. You all can in fact pick this spot, and that is the wavelength. You all could pick this top spot and this top spot. Notice that all my arrows are the same size. It doesn't matter what spots you pick. So long story short, 6 minus 2 is 4. Great. Pretty good with that.
How much is the wavelength if it was like 90 degrees to the way? If it was like oscillating left and right.
Oh yeah, the question is, what if this whole graph was flipped? Do it the exact same way. Yeah, this is a great question. What if this wave, what if I took this entire graph and rotated this graph 90 degrees? How would you find the wavelength then? Whenever we're talking about wavelength, we're talking about the direction it's moving. We're measuring across the direction it's moving, not the direction it's wiggling. The direction it's wiggling is amplitude, the direction it's moving is wavelength. That's a great question. All right. So great, here's a picture of it. Yay, trough, wavelength, crest, nice summary. Okay, something I haven't mentioned, but I'll mention it now. How do you make a wave? This is something you will also have probably seen before and you know about. Pretend this is a string. I wish I had a string. I don't have a string. Pretend I had a string. How would I make a string into a wave? What would I do with my arm? You wiggle it up and down. How do you make any wave? You make something oscillate. What is a wave? Something that oscillates. How do you make a wave? With something that oscillates. How does your voice make a wave? You have a vocal box. You have your vocal cords. They're literally just things that vibrate when air goes across them. Every sound wave, something that vibrates. Every physical wave like this, something that vibrates. How are we going to make electromagnetic waves? We're going to make something that vibrates. So that'll be a future. We'll get to that next class. But that's just to put that on your mind. And you can try to start guessing what you think that thing might be. All right. Using just the units for wavelength and frequency, determine an expression for velocity. Not angular velocity, regular velocity. How fast? Because this wave moves. This wave is traveling in space. No physical objects are moving, but the energy is. Use the units. What are the units for wavelength? What are the units for frequency? Make it work so they match the units for velocity. Is a velocity frequency times wavelength, frequency divided by wavelength, wavelength divided by frequency, or 1 over frequency of wavelength? Actually try it out with the units. Derive it, quote unquote, yourself. All right, give y'all 20 more seconds. All right, in 5, 4, 3, 2, 1. All right, so this is a fairly simple, again, this is kind of a hand-wavy derivation, but it'll help you remember things. The units for wavelength are meters. The units for frequencies are second inverse, which is the exact same thing as 1 over seconds. All right? So, if I want velocity, the units for velocity are meters per second. So if I want the units for velocity, I just multiply those two together. If I multiply meters times 1 over seconds, boom, we get our right units. So there you go. There's the derivation. Again, it's a hand-wavy derivation. But it might be helpful for helping you remember this. So velocity is my frequency times my wavelength. How many waves do I see every second times how big each wave is? Bigger wave, If it's traveling at the same frequency, it's got to be going faster, you know. So maybe an example here to help us maybe intuitively understand this. Think of semis versus cars. If I say I'm seeing 5 semis every second, and I'm saying I see 5 cars every second, if we assume they're like butt up against each other, if we assume that these semis, and that's because these waves, so here's a semi, here's a semi, here's a semi, you know, here's a whole bunch of semis, they're bigger. Whereas here's a car, here's a car, here's a car. If I say that they have the same frequency, meaning in 1 second I see 5 semis, in 1 second I see 5 cars, the semis better be moving faster. Why? Because they're longer. They take up more space. They got to go faster for me to see just as many per second. Just to help you understand where this relationship is coming from. All right, so great. There's the expression. It's written in terms of period as well. If B is a constant, then F and lambda are inversely proportional, meaning as one goes up, the other goes down. And you might say, when would they be a constant? Hold that thought in your mind. It'll be relevant next class. So, very simple expression, but we're going to need this. You're going to see why in a bit. Again, we're going to get mathy pretty quickly. But for now, it's just basics of what a wave is and stuff like that. All this stuff I'm currently teaching you is stuff you've probably seen before. I'm just making sure we're on the same page. All right, so to make sure that second idea lands, 2 waves are traveling the same velocity. One has a wavelength of 300 nanometers. Wave 2 has a wavelength of 150 nanometers. How do their frequencies compare? Does the first wave have twice the frequency of the second? Does the first wave have half the frequency of the second? Does the first wave have the same frequency as the second, or not enough information? Try it out. 2 waves, same velocity, different wavelengths. Find how the frequencies compare. It's very easy to mix up your answer here. Make sure whatever answer you get matches the logic. Is the frequency of one twice as big, or is the frequency of one half as big? A lot of people sometimes misinterpret this first one as saying the frequency of one is half the size. It's not. Answer A says frequency 1 is twice frequency 2. Answer B says the frequency of 1 is half frequency 2. All right, give you all about 20 more seconds. All right, and 5, 4, 3, 2, 1. So I'm going to answer this conceptually, and I'm going to answer this mathematically. Conceptually, I said if they have the same velocity, they're inversely proportional. As one goes up, the other goes down. Wave 1 has a bigger wavelength, so let's use that rule. Wave 1 has twice the wavelength of the other one, so therefore it must have half the frequency. As one goes up, the other must go down. If I have a bigger wavelength, I must have a smaller frequency. Only one of these answers says that wave 1 has a smaller frequency. This is the only one that says it has a smaller frequency. How do we prove this mathematically? We write our equation. F V equals F lambda. Now, we care about frequency, so let's get frequency by itself. We're going to use the technique I've been teaching you all this entire semester. So that's my original. Frequency 1 equals velocity 1 over wavelength 1. Now we write this. The wavelength of 1 equals 2 times the wavelength of 2. Why is this useful? We can rearrange this. So the frequency of 2 equals V2 over lambda 2 equals V2 And you're going to look at this answer a second and be like, that doesn't match. You'll see. 2 times V2 over lambda 1. All right. So you're going to look at this and say, but this isn't the answer. It is if you look carefully. So the frequency of 2 is 2 times the frequency of 1. And you're like, that doesn't match the answer. That's because that's not what that equation says. Rearrange it. Therefore, frequency of 1 is half. Oh, I don't know why there's a lambda there. There you go. Mathematically proven, great. But you all should, again, this is a skill. Can you look at a problem? You actually shouldn't need the math for this if you understand that they're inversely proportional. As one goes up, the other goes down. As frequency goes up, wavelength goes down. As wavelength goes up, frequency goes down. They're inverses. If the velocities are the same, and we'll see next class, most of our situations, the velocity will be the same. Okay, here's another one. This is just general waves. Haven't taught you anything about, okay, there's one thing we need to know. All right, how long does it take for a radio signal to reach you from a radio station, which is 161 kilometers away? We're then going to ask if it operates at 1 megahertz, how many wave crests it sends out every second, how far does the wave travel in a second, what is the wavelength for this wave. There is one piece of information you need to know here that I forgot to include here, but it's one that you're going to have memorized very quickly. It's one that if I give this in a test, I'll give it just like this and expect you to know this, but I haven't taught you it yet, so I'm going to tell you it now. A radio signal is an electromagnetic wave. Electromagnetic waves are light. All light travels at the speed of light. So this is something I haven't taught you yet. It's going to come up in a future slide, but we need it to solve this problem. So it says, how long does it take for the radio wave to reach you if it's 161 kilometers away? I know the distance. I am solving for time. To determine the time it's going to take, I need to know how fast it's going. And we're going to learn 10, 20 slides from now. All light travels at the speed of light. 3 times 10 to the 8. And we're going to actually derive this number. Not from experiments, but from equations, which would be kind of cool. All right, so there you go. That's the speed. So this is a really simple thing. This is a physics 1 problem. Change in distance equals velocity times time. Super easy. You want to know the time? Take the distance, divide it by the velocity. So we're going to do 161 times 10 to the 3, divided by 3 e to the 8. So it becomes 161 over 3. To the power of -5. So this is something you all should, this is also a useful skill that I haven't been really emphasizing, but is very useful. Anytime you will have scientific notation, you can just subtract the values if it's division. If it's multiplication, you can add them. There's a 3 that should be on the bottom. Up there first, yeah.
Oh, that's an E. I'm sorry.
No, you're all right.
Okay.
And yeah.
Is that a 161 or absolutely 6?
It's a 161. Yeah. 161 kilometers away.
Sorry.
No, you're fine. So this is 53.67 times 10 to the -5 seconds. This is 536 microseconds. This is very quick. 161 kilometers is a big distance, y'all. I don't know what it is on the map because I don't know it in let's just get it in miles real quick. I don't have these conversions memorized. 161 kilometers to miles. 100 miles. Oh, it's a nice number in miles. 100 miles away. 100 miles away is... Does that reach the west coast of Florida? Yeah, reaches Tampa. So great, if there's a radio tower in Tampa, it takes less than a millisecond for that signal to reach you. Light is fast. It's the fastest thing in the universe. So that's something we're going to be seeing a bunch of. All right, if this station operates at 1 megahertz, how many wave crests does it send out every second? So this is frequency. Frequency, so this is going to seem a little stupid. This is 1 e to the 6 hertz. What does that mean? That means that every second I am sending out 1,000,000 waves. So what's the answer to be? It's 1,000,000. That is the answer. How many wave crests do I see every second? However many I'm outputting. How many am I outputting? That is the definition of frequency. If you wanted it per minute, you would multiply it by 60, correct?
Is that e times 5?
E to the minus 5. Yep, so great. Part B done. Part A done. Part B done. How far does a wave crest travel in 1 second? This is also very easy.
Where did that number come from?
1 megahertz. Yeah, I'll write that out maybe a bit more explicitly. We haven't been seeing megahertz. We haven't seen the prefix mega up to this point. The prefix mega is 1,000,000, which is times 10 to the 6 hertz. So to convert it to base units, mega, we're going to be working in mega. Fun fact for you all, FM stations, I don't know how much y'all listen to the radio, I listen to it, it's FM or AM. The number literally is the frequency. So when you all turn to radio station 98.6, that's the radio station that's outputting 98.6 megahertz. I think so. Yeah, so if you're ever wondering where those numbers came, I don't know how many people listen to radio anymore. It's kind of outdated at this point. But these waves are passing through you, every single radio station, and when you tune your radio, you're just tuning which frequency that you're listening to. And you're tuning it to the exact number that's on your dial, megahertz. All right, cool. C, how far does the wave travel every second? This is super easy as well. I'm just solving for distance. It's velocity times time. So it's just 3 e to the 8 times 1 second, which means it travels 3 e to the 8 meters. Easy. How far does it travel every second? Speed times time. Easy. All right, part D. What is the wavelength for this? We're going to use the relationship that we just derived. V equals F times lambda. So this one, if you want the wavelength, it's going to be, in this case, C over F. I know I'm kind of cramming this in there. I'm going to shrink everything so I can fit it. There's no reason for me to do a whole new PowerPoint for this problem. C is the speed of light. Yeah, here I'll write it as V for now. Soon enough, we'll never use V over that. So lambda equals 3 e to the 8 divided by 1 e to the 6. This is actually very easy math. This is going to be 3 divided by 1 is 3. 8 minus 6 is 2. It's 300 meters. The wavelength, and this is something that's kind of interesting, radio waves, wavelengths are very large. They're very large waves. Does it really matter? No. What it does matter for, and this is advanced, you don't need to know this, when we eventually learn how to generate these waves, it is useful to have an antenna that is at least half the wavelength, maybe a quarter of the wavelength of the wave you want to generate. This is why radio towers are so big. Has to do with resonant frequencies, and again, beyond the scope of this class. And that's really the only consequence of these antennas is you want an integer multiple to transmit them for resonance purposes.
Where did the speed of light get C from? Why is it called C?
We're going to derive that later. Yeah. Foreshadowing of the future. For now, I haven't derived it. For now, I say trust me, but we will derive it. All right. Here's a question for you all. Which of the following functions describes something that oscillates between two values forever? This one only lets you pick one. There may or may not be more than one right answer. There is more than one right answer. I won't tell you how many right answers. That'll actually be the most interesting thing here, is how many right answers there are. Yeah, the answers here are cosine theta, sine theta, e to the I theta, and e to the theta. All right, give me all 20 seconds. This should not be a hard question for you all. All right, in 5, 4, 3, 2, 1. So part of what I'm about to tell you is going to be something you know. So cosine, I can draw some of these functions, other ones I can't really draw. Cosine oscillates, great. Sine oscillates. Something I'm about to hit you with, that's really weird. E to the I theta oscillates. This is something you might not have heard before. There's something called Euler's formula. Euler's formula says the following, that e to the I theta can be written like this. Unfortunately, I wish that we could spend the time on this. AC circuits actually have a really good description of this. E to the I theta does describe something that oscillates. This is where you all learn about imaginary numbers, and up to this point, you're probably like, what's the point of them? They are used to describe things that oscillate as one application. They actually have physical, when you get the real component of it, it has a physical meaning to it. AC circuits, if you want to look through those slides, there's actually a really big emphasis on the real and complex plane where I talk about that.
Just a general question about waves. Like, how can we make waves that we can't see? You know, like regular.
I can answer that one later, because that one's a little bit, pretty tangential. We'll talk about how we make them in a bit. All right, so, great. They're all the answers. You're going to pick that one, that one, that one. The last one does not oscillate. The last one actually either grows exponentially if theta is positive, or it decays exponentially. So the last term is not oscillating. The last term is exponential growth or exponential decay. But the imaginary result does. All right. We're about to get into some math that we're not actually going to solve too much because it's nothing. All right, great. Here's the wave equation. I'm just going to give it to you. Here's the wave equation. This is a partial differential equation. Where are you going to see partial differential equations? In the class differential equations. I am not going to derive where this came from because it comes from, actually this one I don't think is too bad, but I'm just not going to derive it. I believe it comes from Newton's laws and things like that. Here's all you all need to know. This equation describes waves. This is called the wave equation. If we solve this, we get the wave function. The function that satisfies this is the wave function. Great, wave equation. Notice, one side takes the derivative with respect to x. One side takes the derivative with respect to t. They look the same, but it's about what you're taking the derivative with respect to. We're not going to, again, I'm not going to get into differential equations and how to solve them and things like that, but I will just straight up tell you, sine and cosine are viable solutions to this. We're going to get the expressions, and then if you want to, you can go back and prove it for yourself. But these are viable solutions. However, sine of theta and cosine of theta, hopefully you notice the problem. These are in terms of x and t. So the next few slides is me going from theta to x and t. That's the goal of the next few slides, is to help us understand where this equation is going to come from. Either the I theta is also viable. We're not going to bother with it. We're just going to look at, and we're actually just going to pick one of these. We're going to use sine, but cosine is totally viable. Cosine and sine are the same wave, just shifted by 90 degrees. They're the exact same equation, just shifted. So we're going to pick one. All right. First, we're going to put theta into x. We got two parts. We got to put theta into x, and we got to put x into theta. So I'm going to derive this pretty quickly. It's written out in the next one. I'm going to do it two ways, and then whatever way you like the best, pick that. So first thing we're going to think about, even though this is a wave, we're going to think of like a circle. If you all think of something spinning in a circle, that is the same thing as what a wave does. It just repeats itself again and again and again and again. If you're like, why are we picking a circle? You all did the unit circle at some point. Remember that? Because something that spins in a circle obeys sine and cosine. All right? Why are we going to do this? This is going to let us lean on things I've taught you before. You all hopefully remember something called arc length, because we've used it. S equals r theta. We used it to solve some derivatives. We're just going to call, instead of s, we're going to call it x. X equals s times r. So what we can do here, is we can then resolve this. Sorry, that's not right. What am I doing here? Sorry, that probably didn't make sense. I replaced s with x, everything else stays the same. So from this, you get theta equals x over r. So sine of theta equals sine of x over r. Great. Okay, now we're going to turn this into wave things. When it comes to waves, one of the things we like to describe is, again, think of a circle. Something that's useful for us in a circle is called the circumference. It's how big that circle is. Why is that useful? I don't want r. I do not want r in this equation, because when it comes to waves, there is no r. There is no radius. We're just using this as a tool. So why am I going to do this? Okay, we think of circumference. Circumference uses r, but let's turn this to waves. Let's turn it from circles to waves. Circumference is the length of a full circle. What was the vocab word we used for the length of a full wave? Wavelength. So we're going to replace circumference with wavelength. Using that logic of one full circle is kind of like one full wave. Why is this useful? We can just plug this in now. So sine of x over r equals sine of x over lambda over 2 pi. And boom. So we get, long story short, we get 2 pi over lambda x. So that's, we have turned theta into x. And we have put a lambda in it using this logic. You do not need to be able to derive this, but I just want to make sure, because if I just showed this to you, you'd be like, where the heck did that come from? Where did it come from? Circle. Like we just used a circle. We used the idea of a circle. We used our relationships. Great, we derived it. So you can see that written out here. That's one way of doing it. That's the first way. The second one, for the sake of time, I'm not going to go through it. But this one just uses ratios. Lambda is like x. And 2 pi, how many angles are in one full wavelength? 2 pi. Theta and x, so it's a proportionality, and then you just rearrange this, and that's another way. I like the first one a bit better because we're cool with circles. This one, you got to be cool with ratios. Either works. So great. So this is our first piece. We have now expressed it in terms of x. Here's the problem. My wave is currently not moving. This is a static wave. It is not moving. There is no time dependence here. What happens as time passes? My wave moves. So that's going to be our next step. All right. The wave is moving. Now this one's going to be trickier for me to convince you all, but I'm optimistic I can do it. The wave is moving. So as the wave moves, so we have two waves here. It's the same exact wave, but it's moved. It's shifted. Why am I saying this? At top, when x equals 0, originally, let's just look at this wave. The dotted is the original, so I'm going to kind of color code this. This is my original. When x equals 0, what was the value of my y? 0. You can hopefully see that on this graph. Now, my next wave gets shifted over. It moves. It's a moving wave. It does not just have a value as a function of x. That value changes over time. That's why these graphs, you can't just draw a graph of a wave because that wave actually moves over time. So it moves. So at some later point, at x equals 0, it is no longer 0. It is now 6. This wave is a function of location and time. That's all I'm trying to convince you right now. This wave moves. So we need to care about time. All right. So, at time equals 0, when x equals 2, my value is 6. You'll have to look at the graph and prove that to yourself. Remember, the dotted line is my original. My dotted line is the original. At t equals 3 seconds, that is this orange wave. What different x value gives you the same results? Originally, when x equaled 2, I got 6. Now, what is x equal to give me 6? You'll need to look at the graph. This is just, can you read the graph? That's all I'm trying to practice here. I might have accidentally done that, but it wasn't on purpose. So. Let me see. Yeah, it looks like there's a couple answers. Well, there's only one I really wanted, but whatever, there is two. There is two different answers here. There's one that I wanted to emphasize. Unfortunately, I accidentally put one that... There is more than one answer here. Well, it's fine. It's too late. There is more than one right answer here. There's only one I really wanted to focus on, but it's fine. I'm not going to hold this correct. So this is all building to an argument I want to make. That without making this argument, it might not be intuitive, the results. We'll see. Oh man, the answer's very... All right, I'll give y'all 20 more seconds. All right, we're going to close this one out in 5, 4, 3, 2, 1. Okay. So, again, there's a couple answers here, which is a little unfortunate, but we're just going to focus on one. I'll mark them both correct. So, at t equals 0, it equals 6. The question is basically... When does, or sorry, that's, wrong thing. Here it equals 6. So here, this red line is my red wave. So at t equal 2 seconds, it equals 6. Basically, my question is, how much does the wave, so the wave's going to shift over, you're going to see this wave like physically moves. Think of it like physically moving. And at this time here, it equals the exact same value. Why? Because the wave physically moved to this location. Now, at what time does that happen? 8 seconds. At 8 seconds, I also have a value of 6. So let me just kind of write this out. So sine of 2 pi over lambda times 6. Oh, sorry, 8. It is equals 6 centimeters. Centimeters. All right. Here's what I need to convince you all of. This wave shifted. If I want to go, so these two things are basically equal to each other. So if they are equal to each other, to go from 8 to 2, what do I need to do? Add or subtract? If I want to go from 8 to 2, I'm going to subtract. What am I going to subtract from it? 6. Now that 6 is not the same 6 as the, don't get fixed on that. You need to subtract something. Now I'm going to actually represent it a little bit differently. What does this 6 represent? What does this value I'm subtracting represent? It represents how far I moved. if you look at this graph, we have the distance traveled. How big is this distance traveled? This distance here is 6. So this 6.
On the original or the new one?
This is how far it traveled. This is how far the wave moved. It moved to the right 6. Now all I need to convince you all of, and it's a very simple thing to convince you, Physics 1. What's the relationship between, okay, so that's delta x. What's the equation for delta x in terms of velocity? Here is all I needed to convince you of, to put the pieces together. If my wave moves to the right, I do not add vt. I subtract vt. This is the thing that is slightly counterintuitive. Up to this point, in your life, positive has always meant moving to the right. But if you think about what's happening here, in our equation, if we subtract vt, it moves our wave to the right. If we add vt, our wave's actually moving the other way. There's going to be a few more slides on this to help land that concept. All right, as the wave moves, so this is maybe a bit of a cleaner image. As the wave moves, you can see it shifts. So the wave moved to the, I don't know why. I have this arrow the wrong way. Oh, no, I see what I did. Okay. So the wave moved to the right. Notice that this wave moved to the right. It moved to the right, right? The dotted line was my old school one. How do I fix it? How do I get it back to the original coordinate system? Which way am I going to shift it? Left. If I want to make this one move back, I'm going to move it left. So that's where that negative sign. How do I shift it backwards? I subtract. However much it moved, however much my wave moved, this is my delta x. I'm countering it. This equals vt. So if I want to shift my wave back to make it like the original, I'm not going to add vt, I'm going to subtract vt. You can also shift the coordinate axis, but that one's harder to kind of explain. So mathematically, here's the idea. At a larger x, we end up with the same value. We need to subtract something. That's what we talked about before. To shift it, we're going to subtract it. Remember y'all from Physics 1, x equals x naught plus vt. The x naught is my new. X naught is my original. So if I want to rewrite this in terms of the original, subtract. All of this is just to convince you, and it's going to be on the next slide. All of this, you don't need to this derivation is just to help you understand where this is coming from, because we're going to put all the pieces together now. This is the wave function. This has everything. It has our 2 pi over lambda x, and we're going to subtract or add vt. Why are we adding or subtracting vt? To shift that wave such that the math works. So let me unpack, and then there's one last little thing here. There's something called the phase angle. We're actually going to not really worry about it. It's a really simple thing. The phase angle is just how much you're off, how much your phase shifted, how much your wave. Why does your phase get shifted? There's all sorts of reasons that we're not going to actually get into. So I'm showing you all this with the phase angle, but I'm just going to tell you on the test I'm never going to ask you about the phase angle. But it is something that does show up in this equation. It just tells you sometimes there's external effects that shift your phase, but we won't get into what those are.
Different K than like the spring.
Yes, this is a different wave than a spring. But fun fact, if this was a spring, it would actually be the same K. What if you have a spring? It does oscillate like a wave, and so actually it obeys the same equation. Sine of kx. All right. So, this is the one that's on your formula sheet, the first one. Now, something I'm pointing out here is that W, so there's a couple things here. K equals 2 pi over lambda. This is called the wave number. This is just something we do whenever we have a bunch of constants, a bunch of numbers, we like to combine them together to make our life easier. It's a little cleaner. So let me just write out this function a little bit differently. So we have 2 pi over lambda times x minus plus 2 pi over lambda v times t, and then there's the phase shift. So this first term is just k. You'll often see it written that way. I'm showing you both ways of writing it. What is k? 2 pi over lambda. But sometimes it'll just be shown as k. 2 pi, so this equation right here, 2 pi v over lambda, that is angular velocity. Proving this, again, we can do a little trick. If you all remember, if we think of wavelength like a circle, if you all think of wavelength like a circle, then lambda equals the entire circumference, 2 pi r. The 2 pi's cancel, so you get omega equals v over r. Rearrange this, v equals r omega. That's a definition from physics 1. That is the relationship between angular velocity and regular. So that is why that equation is true, just to prove to you all why. All right. So again, this is probably one of this equation, you need to know how to use it. More specifically, you all need to know how to read it. It's a sentence. You need to know how to read this sentence. What the problem is going to look like? I'm going to give you an equation. I'm going to say find the velocity. I'm going to give you an equation and say find the wavelength. I'm going to give you one of these and say find the amplitude. Can you read the equation? Because this describes every single wave out there. This is the equation for every single wave. And you all need to be able to read the sentence that describes that wave. You can look at a wave and say, oh, it's this big or that. You all need, math gives us precision. And so we need to be able to apply the math to waves. All right, last thing, it's down here, and this is what I mentioned. So this minus plus, why is it in that order? Minus means the wave's going to the right. Plus means the wave's going to the left.
It's like shifting a graph.
It's based on which way you're shifting it. We needed to shift it to the left when the wave was moving to the right. We need to shift it to the right when the wave's moving to the left. This is so again, what would this look like? I'd give you a problem and I'd say find the velocity, and I will care about the positive and negative sign. I'll care about which way the wave's traveling. Direction matters. Can you read the equation and determine which way things are moving? So great. That is the wave function. Literally every single wave can be described by this function. That's the value of it. And we just spent a bunch of slides deriving it. Okay. Case in point. Here's a wave. What's making this wave? I don't care. What's this wave doing? Well, that describes what it's doing. What is this? It's not an electromagnetic wave, I can tell you that. It's some random wave. I don't care what it is. Water wave, wave on a string, sound, I don't care. It's a wave. Find the amplitude. Find the period. Find the wavelength. Find the wave speed. Find the phase shift. Can you read this equation and pull out meaningful information from it? That's the goal of this. Math is a language. Can you read? It sounds rough, but that's what I'm teaching you all how to do here. So, amplitude is going to be the easiest. The amplitude is literally the first thing here. So that's just 3 centimeters. That's easy. In fact, before I even do any of this, let's actually write. This is something very useful. When you all see this wave equation, something to get used to, it's a function of x and t, where I'm located, and how much time has passed. You care about both things because the wave moves. And just to make sure you are cool with what we're doing here, when we're solving for this, we're solving for y. We're literally solving for how quote-unquote tall this wave is at that location at that time. Just so you keep track. What am I even doing here? What does this equation do? It says if I plug in some x and some time, I will find how tall it is there. That's what this wave equation does.
What if the y value is negative?
That's fine. Yeah. It goes either way. Yep. And it will be negative. At sometimes it's negative, at sometimes it's positive. Something I'm going to eventually convince you all of is this y is actually a vector. Eventually. All right. So amplitude times sine of 2 pi over lambda times x minus vt plus phi. And we're going to make that minus plus. Let me actually make sure this is the one I gave you on the formula sheet. It is. There it is. So this is the one you want to be able to that's what's going to be given. You need to be able to go from that to whatever, or whatever's given to that. All right, so amplitude, really easy. A equals 3. Now, be careful. The units here matter. I know they kind of got bumped to the next slide, but they're centimeters. This wave equation will not always be measured in meters. Actually, very quickly, we're going to soon find it's going to be measured in volts per meter or Tesla when we get to electromagnetic waves. All right, great. The period. The period is the time it takes for one full wave to kind of pass by.
1 over F.
It's going to be 1 over F. So there's a few ways to get this. There's a few ways we can get this. So you can remember that T equals 1 over F. Then the next question is, how do I get F? That's one way of thinking about it. Another way you all can think about this is the period. It's the time it takes for one wave to pass. So why am I mentioning that? I'm going to write something a little funky here. Delta x equals Vt. I'm going to rewrite this now as lambda equals velocity times period. Why am I saying that? How far does a wave travel during one period? One full wavelength. How much time passes when it is one period? One period. These two equations are the same thing. So this is another way to get the answer. So T equals lambda over V. Distance divided by velocity gives me time. What's the distance? One wavelength. What's the time? Period. What's the velocity? So pick your favorite. I'm going to use the second one because it's easier to get from this expression. So if I take my original function, I'm going to just kind of match some things here. So how to write this out? I'm going to write this another way. A times sine of 2 pi over lambda x minus plus 2 pi over lambda v times t plus phi. I just transferred the 2 pi over lambda in there. Why did I do that? That value equals 0.4. That value equals 2. The original equation. Yeah, no, you're good. Actually, I'll highlight that. This equals that. This equals 2 pi over lambda. All right. That's weird. What the heck? Well, the reason I'm really confused is I just highlighted something on my... Oh, blue is just not visible for you all. Sorry. I'll make it darker. Now it's hard to see. All right. Try 3. We'll do green. Sorry, the contrast for these projectors is unpredictable for me. On my screen, it looks different than this screen. All right, great. Why does this matter? So this is going to be maybe a bit more involved. So then, therefore, 0.4 equals 2 pi over lambda. So we can solve for lambda. Lambda equals 2 pi over 0.4 equals something. 2.51 centimeters. Great. Now we're going to solve for V. 2 pi over lambda. Oh, and this is very important. Negative times V equals 2. That's a great question. Why did I make it negative? Because this tells us it's the inverse of that. This wave, which way is this wave traveling? Left. This wave is traveling to the left. Because it's a plus, remember that it's the opposite. Yep. So the 2's cancel. So V equals pi over lambda, which we have the numbers here. So pi divided by the answer I just got is 1.25. Now, you got to be super careful here. The units here are centimeters per second. Why? Because my wavelength was centimeters. Now, thankfully, it's not going to really matter. So now if we go back over here and we just plug in our numbers, so we get 2.51. Notice I didn't convert to meters because if they're both in centimeters, it'll cancel out. Divided by 1.25, and we get roughly 2 seconds. Great. Wavelength, I already found it. That's done. Wave speed, I already found it. That's done.
Would the velocity be negative?
Would the velocity be negative? Yes. Yes, thank you for reminding me of that. This should be a negative velocity. All right. And the phase shift, that's just pi over 10. That's also really easy. So the rest of this is actually kind of done. We solved for everything in the process of solving for this. So yeah, this is actually a great point that I want to get to. There's the wave function. Make sure y'all can read it. There's going to be a ton of practice problems on this. Period's always positive. Period's always, it's the time it takes for one full wave to pass, so we don't care which way that wave goes.
So for recitation, we don't have to go to a